Hello everyone, welcome to the second video of TFHE series. In the first episode, we covered we gave an introduction and covered the morphology of FHE ciphertext and and touched on LW ciphertext, GLW ciphertext, and some sort of complicated ciphertext like GLWE and GGSW ciphertext. And in this video, we will see some simple operations on TFHE ciphertext. Simply in this video on GLW ciphertext, what we will see much more complicated ciphertext operations more in the upcoming videos. So let's start. Let me quickly check if everything is all right. Yeah, because this is my second recording as my iPad stopped working while I was calculating some ciphertext sums. Okay, so in this section we recall the simplest operations that can be performed over ciphertext, namely addition and multiplication by a public polynomial, which we call scalar multiplication. Then we introduce the sample extraction procedure, which converts a GLW ciphertext into an LW ciphertext, and show how this can be used to construct an efficient public key encryption scheme. So we're not gonna dive deeply into sample extraction procedure this video. It will be the topic of the third video, the next one. But yeah, it's really important because of its use in both efficient public encryption scheme, constructing it, also in the bootstrapping procedure as well. But as I said, in this video, we will mostly cover the linear operations. So the first linear operation is obviously summation, or we say this add function. And it can be done over ciphertext to add them up homomorphically. Informally speaking, the addition of two ciphertexts is done by performing coordinate-wise addition modulo q. The resulting noise will be the sum of the two noises because of the linearity. Formally, algorithm 3 defines how to add two ciphertexts that are encrypted under the same secret key. So this algorithm 3 simply takes two inputs because of the fact that index set consisting only 1 and 2, and in the input section we clearly see we have two ciphertexts, CT1, CT2. They are both GLW ciphertexts of plaintext M1 and M2 respectively, and we're gonna have an output another ciphertext CT3 that is supposed to be the encryption or GLW encryption of M1 plus M2. So addition of ciphertext should give the underlying addition of plaintext. And our algorithm simply is a for loop, simply adding every single entry of underlying GLW ciphertext and assigning them into a new ciphertext we call CT3, and simply it gives us the summation. So we simply add AIs and BIs, and at the end assigning them into the corresponding entries of CT3, and that's it. Theorem 1, GLW addition, simply says the same thing, but making it more formal from the mathematical perspective. Obviously, we're not going to do noise analysis, as this course or this playlist is mainly focused on the practical aspects of the scheme. But I do think it would be useful to understand how these things work when it comes to use some toy examples. And in this one, let's have a toy example and see how these things simply work. I need to check the iPad constantly, as it's impossible to know when it's gonna stop working. So yeah, okay. Let me see the numbers. Okay, first things first, we need to first choose the parameters, right? So let's start with the Q, the ciphertext modulus. let's say 64. Plain text modulus is, let's say, 4. And then we have the scaling factor delta being equal to 64 over 4 equals to 16. Another parameter is obviously n, and let's set it to 4 and k to 2. So our polynomials will be like, we'll have 2 entries, and our polynomial modulus, let's say, will be 4. So we're not gonna have x to the 4 anytime. So then we have 2 messages, right? We need 2 messages to encrypt and add. So let's say the first message m is equal to -2 plus x minus x cubed, which is an element of RP, and our other message m prime equal to x plus x squared minus 2x cubed, which is also an element of RP. When we need one thing more to perform the encryption, yeah, it's the secret key. And our secret key will be a vector of polynomial. In our case, as k is equal to 2, we will gonna have 2 polynomials as vector entries, s0 and s1, and let's set them to x plus x squared, comma 1 plus x squared plus x cubed, and this will be an element of r squared, right? Okay. So what do we have now? We have these messages, and maybe we can add them up, right? And to compare the end result. So let's say m plus being the summation of m and m prime. So we have -2. We have -2x as because of the modulus. We have x squared, and we have minus x cubed plus minus 2x cubed, which is actually minus 3x cubed, but because of the modulus, it's plus x cubed. All right. Okay, so let's see. I need to quickly check my notes. Okay. Let me go to a new page. Okay. So now we need to encrypt these messages, right, using GLWE encryption. But let's choose our mask vector. Of course, this should be randomly sampled, but this is a toy example, so I'm just making it up. It's a kind of a pseudo randomness, I say. So we're gonna have a 0 and a 1, obviously, and let's set them to 17 minus 2x minus 24 x squared plus 9 x cubed, comma, minus 14 minus x squared plus 21 x cubed, which is an element of RQ squared, obviously. And we need also the noise, and let's set it to -1 plus x plus x cubed from RQ. And this is our randomness. Now we have everything we need. So we just need to apply, the encryption procedure. But first, maybe we can also determine the corresponding, variables for m prime as well. So let's say a prime vector is equal to a0 prime comma a1 prime is equal to minus 8 plus 15x plus 3x squared minus 30x cubed, comma 23 minus 16x plus 27x squared minus 4x cubed, which is also an element from RQ squared polynomial ring. And corresponding noise polynomial is equal to x minus x squared minus, sorry, it should be minus x cubed from RQ. Okay, now we have everything we need. These are masks and noise randomness, and now we're gonna calculate the body of the ciphertext. Okay, let me go to, okay. Okay, interesting. I don't know why. Okay. Now, I mean, OBS is too heavy for my computer, so okay. Now we're gonna calculate corresponding bodies. So let's say body gonna equal to a times s, this is a dot product, plus m plus e, and start calculating it. I mean, obviously I'm not gonna calculate one by one because of the moduli. It would take quite a long, so that's why it's always good to have some pre-prepared notes. It's gonna simply be equal to a0 s0 plus a1 s1 plus m plus e, right? So henceforth, when you perform these calculations, you're gonna have minus 31 plus 5x minus 21x squared and plus 30x cubed from RQ. For B prime, you will have obviously a prime vector dot s prime vector plus m prime plus e prime. That is gonna be equal to a0 prime. Means okay, s0 prime plus a1 prime s1 prime plus m prime plus e prime. And when you perform the calculation, it's supposed to be equal to minus 25 plus 11 or 12x squared, or 12x or x squared minus 12x cubed from RQ. Obviously, these are all, like, previously done calculations, but if you want to repeat the calculations just to make sure about the results, also getting better and better, and improving your like FHE intuition, you need to be careful about the fact that all these calculations were done polynomial modulo x to x to the 4 plus 1. So, and also the main modulo q, which was equal to 64. Okay, so now the next step is to perform the homomorphic addition, right? And that was simply adding the corresponding entries one by one. So let's calculate let's calculate the entries one by one. All right, so let's start by a0 sum. That is gonna be equal to a0 plus a0 prime, and that is equal to 9 plus 13x minus 21x squared minus 21x cubed from RQ. A1 plus N3 is equal to A1 plus A1 prime, and that is equal to 9, again, minus 16x plus 26x squared plus 17x cubed from RQ. And finally, our B plus is equal to B plus B prime, and that is equal to that is, yeah, 8 plus 5x minus 9x squared plus 18x cubed. Yeah, like, because of, saving time, I didn't calculate everything in this recording, but I mean, just to point out some important, calculation bottlenecks, we can cover the example of, like, adding b and b prime, right? We had minus 31 and minus 25. We added them up and we got 8. Why so? Because when you add them up, you have 56, right? But 56 is equal to actually, or is equivalent to 8 modulo 64. So, and everything in the other, polynomial terms is the same. Nothing more complicated. All right, let's go through to another new page. We have these entries. Okay, so let's now decrypt, just as we learned in the previous video. So we gonna calculate B sum or B plus. I don't even remember what I call that at the first place. But let's say B plus. B plus minus summation of AI dot SI, or obviously AI plus, and that is equal to 31 minus 30x plus 15x squared plus 16x cubed. And then we're gonna divide it by the scaling factor and then round it, right? So when we divide it by our scaling factor 16, we have, let's write this way, we have also let's round it, we have minus 2 minus 2x plus x squared plus x cubed, and that is element of our P, right? The plain text modulus, which is exactly, sorry, yeah, the plain text summation, minus 2 minus 2x plus x squared plus x cubed. So homomorphic property is actually preserved. All right, let's get back to the notes in the handbook. Okay, we have another algorithm for addition of a public constant. Let's see what it is. By having one of the input ciphertexts, say CT2, in algorithm, what is this, 3? Be trivial encryption of a public constant that has been suitably encoded, we can add a public constant to a GLWE ciphertext without increasing the noise. Oh, I see. Now, let's assume we have a ciphertext, with a noise, and we can add a public constant, like, adding 2 to a ciphertext, but as a number, not an encryption, and that would not increase the noise. That's the main point, because we don't even need it. We don't even like need adding noise, as this constant is public. We don't want to mask it. We don't want to hide it. But before explaining how to multiply a GLWE ciphertext with a polynomial, let us see what happens when we multiply a GLWE ciphertext with a power of x. We call this operational rotation, which is really important though. So let's see our algorithm. The context is obviously a secret key, and assuming this in is input, an input ciphertext from RQ to k plus 1, and so yeah, we have an input. We have three inputs. Yeah, a ciphertext, maybe two inputs. Yeah, ciphertext with underlying message m and an integer omega to multiply it. This integer is public, and the output will be another ciphertext, and that is gonna be the encryption of the public integer multiplied by the message. So this we have another linearity, right? Okay, wait. Okay, we have another linearity. So what is it? So we have a message, and we have a ciphertext. Let me write it bigger, which is the encryption of m, and we have a number omega, and we're multiplying this omega by the encryption of m, but that is also equal to the encryption of the multiplication of the message and omega. This is obviously a homomorphism. So let's see how it works. So it should be quite simple. We have another for loop, obviously, as we have more than one entries within our ciphertexts. And we simply multiply the x to the public integer by each entry. Okay, the theorem stays the same thing. We can do another toy example for this as well. But I'm just thinking if we should do it with an integer or maybe a small constant polynomial, because we also need to cover that, right? Multiplication between a GLW ciphertext and a power of if it is a theorem, and scalar multiplication. Okay, no, this is more comprehensive. So let's do this. Let's do this. So we're gonna be given a GLW ciphertext CT input or CT, and we're gonna be given a public polynomial, and we're gonna multiply the ciphertext by the polynomial. So okay, and we have an input of GLW ciphertext and a integer polynomial from that x, and we're gonna have a ciphertext output, again homomorphically computed. So it's gonna be the same thing if you multiply it with by the message and then an encrypt, or encrypt and then multiply, thanks to the homomorphic property. So let me find my toy example. Okay, so we're gonna use the same parameters, like q being 64, p being 4, delta being correspondingly 16, and n being 4, and k being 2. And let's use the same ciphertext with the first one. So let's say still eraser. We have still c equal to ab equal to, this is a vector, a0, a1, b, and let's make it equal to the same value, 16 minus 2x minus 24, x squared plus 9x cubed, comma, minus 14 minus x squared plus 21x cubed minus 31 plus, we have a comma here. We have a comma here, 31 plus 5x minus 21x squared plus 30x cubed, and this is obviously from RQ3. The first two entries are from the vector A, the mask, and the third one is the body B, simply. Okay, now let's have and this ciphertext encrypts the message, the same message, -2 plus x minus x cubed from RP under the secret key s is equal to s0 s1, which is equal to x plus x squared comma 1 plus x squared plus x cubed from r squared, and error being -1 plus x cubed from rq. All right, again we have all we need. So now let's choose a polynomial to multiply. Let's call it, what was this, alpha? Yeah, capital alpha, right? Please, yeah, let me know if I'm wrong. -1 plus 2x squared plus x cubed from our ring R. And now we're gonna multiply this with the message, and let's call it m, let's say times, or dot, let's say m dot. M dot is equal to m times, alpha, which is equal to 1 plus x squared plus x3. I mean, it's so obvious that these polynomials are, chosen purposefully, which actually worked quite well. And now we're gonna perform this multiplication homomorphically and check if it's true or and satisfies this plain text computation. So now we're going to multiply the components of ciphertext C by our public polynomial alpha. Okay, so let's call it a0 dot, and that is equal to alpha times a0, which is actually equal to -31 plus 8x minus 15 x squared plus 4x cubed from RQ. A1 dot is equal to alpha times A1, which is equal to 16 plus 23x plus 16x squared plus 29x cubed from RQ. B dot is again the same, alpha times B, and that is equal to 4 plus 20x minus 7x squared minus 13x cubed from RQ. So we have this new ciphertext C dot, which is equal to A dot 0 or A0 dot or A dot 1 and B dot. Now let's decrypt to verify that the first result was, or this result we're gonna be correct. To decrypt, as we did in the addition part, just the compute B dot minus summation of AI dot SI, this is obviously dot, which is 16 plus 13x plus 13x squared plus 16x cubed in RQ. Now we need to perform the dividing by the scaling factor and then rounding. So it is, let me do it this time. We're gonna round the polynomial this polynomial 16 plus 13x plus 13x squared plus 16x cubed after dividing it by the scaling factor 16. And when you do it, when you divide it by 16, we're gonna have 1 plus 13 over 16 is 1 when you round it, x plus the same x squared, and when you divide 16 by 16 is 1, no need for rounding, another 1, so we have 1 plus x squared plus x cubed in RP, the plaintext space, so which is again exactly what we had in the first place after calculating the multiplication on the plaintext versions. So all these decryptions worked because the error coefficients were all smaller than the scaling factor by 2. But we need to be careful that the error actually increased after the polynomial multiplication, and we need to limit this growth at some point, which we'll see in the upcoming videos. So let's see what we're gonna cover in the upcoming episode. Yeah, fast polynomial multiplication, and yeah, linear operations on GLWE and GGSW ciphertext. Yeah, as I mentioned in the earlier part of the video, the operations on these ciphertexts will be, it will be again straightforward, but it will be more calculation heavy because of the morphology of these ciphertexts compared to GLWE ones. And then, yeah, we will continue with homomorphic dot product. So thank you so much for watching the video. I've tried to explain how, linear operations like addition and, like scalar multiplication on GLWE ciphertext in this video. I hope it was useful and helpful and maybe even fun. So if you have any sort of feedback regarding the series, like the particular part of any video, or some points where things didn't make that much of sense, please let me know. So yeah, thanks for watching.